day 3, and the points that I want to convey today. So one of them is where we left off yesterday, which is why B1/3 minus 3 infinity is sharp, and this will follow from something or lead us to something which I call the Goldilocks rule. See, which tells us exactly how much intermittency to use when we construct these functions. And after seeing the Goldilocks rule, then I can explain why we need wavelets series. Why wavelets? Okay, so let's set up our iteration again. So so we have the relaxation of the Euler equations. And I often refer to this first equation as ER for Euler-Reynolds. And then we have the relaxation of the local energy inequality. And on the right-hand side, we have div phi q plus rq uq. This rq was 3 by 3 and symmetric, and this phi q is just the vector field. And we also had bt plus uq dot obla, 1/2 trace of R. All right. So
is there any other relaxation that is used? I mean,
that's a very good question. So I'm going to revisit this relaxation again because I didn't quite explain why it looks the way it does, and I really want to. Okay, so the Q refers to lambda Q, which was our frequency parameter. And in terms of the frequency parameter, we have an amplitude parameter, and the beta here corresponded to the regularity that we were aiming for. So we saw as B approaches 1 from above, beta approaches whatever its maximum allowable value is from below. And in terms of these parameters, we have inductive assumptions. So we said that if I just look at the size of RQ in L infinity, it should be delta Q plus 1. And when I take space derivatives, this is the space frequency, and so every space derivative costs a factor of space frequency. And similarly, for the phi q, it should scale as the 3/2 power of RQ, because RQ scales like velocity squared, phi q is going to scale like velocity cubed. So I should see here delta q plus 1 to the 3/2 lambda q again. And we have an inductive assumption for the size of the velocity field. So gradient of the 1 plus n in space of uq was delta q to the 1/2 lambda q to the n plus 1. All right. And we constructed this velocity field iteratively, and our velocity increment we call WQ plus 1. This was UQ plus 1 minus UQ. And you can think of that as the projection on frequencies in between lambda q plus 1 of whatever the limiting solution u is. But when we built this WQ plus 1, we built it, well, we first split up into portions which correspond to the Euler-Reynolds and the relaxed local energy inequality. And for the moment, I'm just ignoring interactions between these two. We'll deal with those maybe tomorrow. But let's just assume that they don't talk to each other at all. And I define the velocity increment using these two pieces. All right, so what are these two pieces defined by? So, well, we can just write it. So this was like minus 2 RQ to the 1/2. When we did the simple example, we saw that the scaling was like the square root of the stress. So I think in the simple example, I put an E1 there. And then we multiplied by some high frequency function of Y. So that I have a shear flow here. That's a stationary solution. And we didn't talk much yet about this WQ plus 1 phi, but the principle is pretty similar. So I'm going to put the cube root of phi q, and I'm going to put P1 again. And then just for the moment, I'm not going to tell you exactly what shear flow I'm putting here. I'm just going to say it's some function, some smooth function, which I've dilated by the high frequency lambda q plus 1. And as we'll see, it's important that this smooth function has cubic mean equal, I think in this example, to 2. Okay. So my plan is to leave this board here. So try and hold me to that, because this is sort of the baseline of what we're working with. And I guess there's one thing I should add, which is that with this definition, you get that the norm of a derivative of WQ plus 1. So if I have square root of the stress, that's half of the delta. Cube root of the phi q, that's another half of the delta. So half of the delta. And every space derivative costs the big frequency, which is lambda q plus 1. All right. All right. Very good. All right, so let's look at the relaxed local energy inequality a little bit, so that we can see what happens when I add WQ plus 1 into the system. So I'm writing down what I expect to find on the left-hand side of this at step Q plus 1, but I'm not doing anything with the pressure for the moment, because we'll deal with the pressure later in the week. For the moment, I'm just going to leave it at EQ. And we're going to divide this up into pieces. So there's definitely going to be all the UQ terms, which I know give me exactly the stuff on the right-hand side. So let's first write out those terms. So I'm going to have divergence of phi q. I'm going to add some other stuff to it in a second. I'm going to have divergence of RQUQ, which I'll split up as divergence of RQ dot UQ plus RQ contracted against gradient of UQ. All right, and then I'm going to have this term. So UT plus UQ dot nabla 1/2 of trace of RQ. And now I need to fill in some of the rest of the blanks here. So what am I going to put with phi q? I'm going to put the cubic interaction of WQ plus 1 with itself coming from this term. So I'm going to put 1/2 WQ plus 1 mod WQ plus 1 squared. What am I going to put with this term? I'm going to put a different piece of the cubic interaction, which corresponds to 2 factors of W beside the divergence, dotted with UQ. And the reason I've set it up this way is because I know that RQ is equal to the projection onto low frequencies of WQ plus 1 tensor with itself. So let's just say W tensor W. So I've paired off these 2 terms. Now I ought to pair off this term. So I'm going to pair this term with the part of the cubic interaction that again has 2 copies of W, but the derivative lands on UQ. And I paired this up like this for the same reason that I paired these 2 ones together up here. It's because the low frequency part of WQ plus 1 tensor with itself is exactly RQ. And we called this one, this was the relaxed local energy inequality Nash error that we looked at yesterday. Right? Because all that's going to be left is the high frequency parts of WQ plus 1 tensor WQ plus 1 contracted against DQ. All right. What am I going to pair with trace of RQ? Well, the natural thing to do is modulus of WQ plus 1 squared. Because if WQ plus 1 tensor WQ plus 1 is equal to minus RQ at low frequencies, then the modulus of this at low frequencies is equal to the negative of that. All right, so I'm pairing these 2 together. And there's a few remaining terms which I'll just write out for the sake of writing them out, although we will use them in a second. So there's one, and the other one is this. All right, so this is what you get if you just distribute all the different terms from this thing at level Q plus 1, and I've arranged it in a way which will be advantageous for us. And What did we see yesterday? We saw that the RLEI Nash error was not so good in C alpha. So RLEI Nash, this gave us C 1/4 minus as the best possible. All right. I want to say something now about this first term. I guess we'll box this. So this first term, I'm going to call RLEI oscillation because it's the nonlinear. It's the nonlinear error term that comes from the cubic interaction of the high frequency thing with itself, the highly oscillatory thing with itself. And let's use the same simplifications that we used yesterday when we treated the Euler-Reynolds oscillation error. Namely, let's assume that this phi q is only in the E1 direction. Let's just put it E1 times phi q, and now phi q is a smooth function. It's a scalar. And let's only consider for the moment what happens when the WQ plus 1 phi lands inside of here. I don't want to treat the couplings for now. So let's just put 1/2 WQ plus 1 phi, WQ plus 1 phi squared. So this is a squiggly because I've ignored some terms. All right, but let's just treat what we have here. So I set this thing up to be a shear flow with velocity field in the E1 direction. So and if I cube, or if I take, 1/2 the modulus of WQ plus 1 phi squared, and I multiply by WQ plus 1 phi, what will I have? So I'll have a minus phi q, and then I'll have this bar theta cubed. All right, and now we see why it's important that we normalize this thing in L3 to have size 2, because I can split up this high frequency function cubed into its mean and the other term. So I'll write projection off of the mean as P not equals. And by the choice that the mean was equal to 2, now this cancels with this. And by the fact that rho only depends on y, all that we have left is dx by q, projection off of the mean of this thing cubed. And this is sort of a paradigm for what to expect in these nonlinear error terms. the nonlinear errors are always basically gradient of the previous error multiplied by a projection off of the mean. So projection on the non-zero modes of some high frequency shear. This is always how these nonlinear errors come form. All right, and now let's check the size. So let's define the oscillation error part of phi q plus 1 as the inverse divergence. And now the size. We use our usual heuristics. So inverse divergence gains the frequency, lambda q plus 1 inverse. Dx phi q costs delta q plus 1 and 3/2 lambda q. And I would very much like for this to be less than the size of the next phi, which ought to be delta q plus 2 to the 3/2. All right, let's do our usual arithmetic trick. So maybe I'll add over here that with this definition, lambda q plus 1 equals lambda q to the b. That's always how we simplify these inequalities when we want to compute what beta ought to be. Okay, so delta q plus 2 to the 3/2, that's going to give me a b squared, right? Because it's defined in terms of lambda q plus 2. And it's to the 3/2, so it's going to give me a 3 beta. And I'm going to move it onto the left-hand side. So it's with a plus sign. Then the delta q plus 1 gives me 3 beta b. And the lambda q plus 1 and the lambda q, I move over to the other side and I get b minus 1. All right, so I just wrote everything out in terms of lambda q and compare the exponents on either side, and this is the inequality that I need to hold. And so this is true if beta is less than 1/3. Okay. So we see that the current oscillation error is sharp in C1/3. All right. Let's clean up now this expression a little bit. So let's check these off. So this one we just did. This one we talked about yesterday. So these are part of the phi q plus 1. I'm going to ignore both of these for the moment. So everything in green, let's say, we've just thrown into the next current error. You can treat these in a way similar to what I've done with these things, but it's just more the same. So let's see. And this one I'm also going to ignore for now. All right, so we're doing really good. We're ignoring all the errors. Okay, let's not throw that one in there. Let's Yes, let's keep this one and this one together. So this one, this is like divergence of the Reynolds oscillation error, right? Because the Reynolds oscillation error is the difference between, it's the sum of div RQ and div W times W. So this one is the oscillation error part of RQ plus 1 dot UQ. And this one is the other two parts of the RQ plus 1 that I didn't, well, I guess I talked about this one. So I did talk about Nash. So this is the divergence of RQ plus 1 Nash. And this one is the transport one. It's the other one. So let's put P N for transport and Nash. So this is RQ plus 1 transport. And that is tiny writing, so I have to apologize for breaking my promise to write large. All right, and this is dotted into UQ. All right, so when I collate these two things together, what do I have? I have div of RQ plus 1 dot UQ. And what would I like to find on the right-hand side of this mess? Well, what I would like to find is div of phi q plus 1 and div of RQ plus 1, UQ plus 1. And I used the version of this in here, and I'm not going to worry about how to get the Q plus 1 version of this in there for now. So let's ignore this term and just focus on having these terms, which I don't exactly have. What am I missing? I'm missing gradient UQ against RQ plus 1. And I'm missing if RQ plus 1, WQ plus 1. Now this is equal to this. Right, because this gives me the UQ against RQ plus 1 inside of the divergence, and this gives me UQ plus 1 minus UQ against RQ plus 1 inside the divergence. So these now are two new error terms, and let's check the size, at least, of this one. So let's check size of RQ plus 1, WQ plus 1. It's already inside of a divergence, so I don't need to do anything there. I'm just checking the size of this. How big is this? Well, RQ plus 1 is going to be delta Q plus 2. And WQ plus 1 is delta Q plus 1 to the 1/2. I'd like this to be less than delta Q plus 2 to the 3/2 in order to go into the next error. But this is never going to be true. Never going to work, right? Because I have a factor of delta Q plus 2 which cancels. And then I'm comparing delta Q plus 1 and delta Q plus 2. Never true, right? Because the deltas are decreasing in Q. All right, so just store this away in your memory for a minute. And just remember that this will never work in C alpha. If I want to close this estimate somehow, and this is what the paper of Camilo and Shinju do, they make this term here artificially small so that they can help compensate and get you a delta 2 plus 2 on the 3/2 on the right-hand side. But you're never going to be able to get this to work without some sort of artificial smallness introduced somewhere in this.
Especially, you mean no intermittency, but something else.
No, I mean, you secretly make this thing smaller than delta Q plus 2, so that when you hit it with delta Q plus 1 to the 1/2, it's actually delta Q plus 2 to the 3/2. But if you cheat and try and make this smaller than delta Q plus 2, it's like saying the Reynolds stress is secretly smaller than I know it actually is. And we know that the Reynolds stress is already butting up against the 1/3 threshold. I can't make the Reynolds stress secretly any smaller, because if I could beat Onsager's original conjecture, right? I can't make the Reynolds stress any smaller than it already is.
So they are like having additional assumption on this, which is below the rest of the iteration. I mean,
no, it's just a. So instead of writing delta Q plus 2 here, they actually write out some quotient of other deltas and lambdas, and then they enforce some artificial conditions between the deltas and lambdas, which are not commensurate with 1/3. Okay. Now, what we're going to do is claim that intermittency fixes this problem. All right. So, wait. In an L3 iteration, P plus 1, W plus 1 is the right size. And notice that I haven't said that it's delta Q plus 2 to the 3/2. And that's the reason for that is because the right size is something that we have to figure out. It's not going to be what your first guess might be, which is, oh, it's just delta Q plus 2. All right. So I can't give you a proper proof of this claim in the sense that well, what do I want to show you? I want to show you that this is the right size fits with the 1/3 minus 3 infinity. That's what I want to convince you of. All right, so let's try and do proof of this. So I have to tell you what's changing when we compare the L3 iteration with the L infinity iteration. And the first thing that changes is that I get rid of the cosine and whatever this thing is, and I replace them with something which is intermittent. Replace cosine bar theta with an intermittent shear. And what does intermittence mean? Well, I'm going to call this intermittent shear WQ plus 1, and it's going to depend on a parameter RQ, which is the intermittency parameter. It's going to be a shear flow. So it will point in the E1 direction and oscillates, or the EX direction, or whatever you want to call it, and oscillate in the Y and Z directions. And it will have frequency support in the range lambda q plus 1 RQ up to lambda q plus 1. All right, so what's the idea here? The idea is that cosine is totally concentrated in frequency. So exchange frequency concentration for a smearing out of frequencies. Or a smearing out of frequencies. And when you smear out the frequencies, if you do it correctly, you may expect that the spatial support will conversely start to shrink. So this will concentrate spatial support. And the picture here is that here's cosine, no spatial support concentration at all, and perfect frequency support concentration, versus whatever this W looks like, which is going to be something like this. This is the difference between homogeneous and
now that this can be realized by location. I don't know. You see the
absolutely. So the comment that Jan made is that an example of an intermittent function is the Dirichlet kernel. I won't use the Dirichlet kernel. I'll use something which is a little more convenient.
Yeah, my only point was that if you are wondering what is the frequency support on this of this
guy, that you can think about first approximation in this, and then you know the frequency support needed.
Yeah, I suppose you can think about it that way, although I don't. All right, now what are the estimates that we can expect on some function like this? Well, let's rescale back to unit scale. So let's divide by lambda q plus 1 in the y and z variables. Now, if I take something which is frequency support in between lambda q plus 1 RQ and lambda q plus 1, and I scale it by lambda q plus 1, this thing is going to have frequency support in the set of frequencies which are, let's say, 0, less than or equal to the size of the frequency, less than or equal to RQ inverse. That's what happens when I rescale this function by lambda q plus 1. And from Bernstein, for a function which has frequency support in a ball and oscillates in two directions, I know that the LP prime norm for p prime greater than p is less than or equal to the volume of the set of frequencies, which is RQ minus 2 times 1 over P minus 1 over P times W RQ L. So this is the Bernstein estimate. And notice now I've introduced some dependence on P, and this means when I define WQ plus 1 phi, I want to use something as my high frequency function, which is normalized in L3. So I'm going to define this thing to be WQ plus 1, capital WQ plus 1 phi, basically times minus 5Q to the 1/3, where the LP norm of this function is like RQ to the 2 over P minus 2 over 3. And I've chosen that scaling because it's consistent with plugging P prime equals 3, so that I have something which is normalized in L3, and this then is the estimate effect. And for WQ plus 1R, I'm going to define it, right? This was my heuristic definition, the square root of the stress times something high frequency. And the LP norms of this thing are going to be different. I don't want to normalize in L3. I want to normalize in L2. And if I want to normalize in L2 and be consistent with this Bernstein, then 2 over P minus 1 is the right thing. All right. So that's the first step, is getting rid of the homogeneous sines and cosines that we've been using and replacing them with something which is intermittent. And we see right away that the intermittency behaves differently in the L2 normalized object as compared to the L3 normalized object.
I'm a little bit confused about the volume. So shouldn't like just RQ minus 1 to the 1P minus 1Q prime times 3, for instance? I mean,
I'm only oscillating in 2 variables.
okay, sure.
So that's the 2-dimensional burst.
Sure.
All right, so with this in mind, we now need to check what the correct size for R2 and phi is. And I guess also WQ plus 1 and now WQ. So all this inductive stuff that we had set up in L infinity, I have to set it up in L3. All right, so let's do RQ first. So we know that minus RQ is equal to, roughly speaking, the low frequency interaction of WQ plus 1R with itself. And if I'm doing an L3 iteration, then I'm measuring WQ plus 1 in L3. That's what I want at the end of the day, are L3 estimates. Which means that if I take something which is naturally measured in L3 and I square it, the natural measurement for RQ is in L3 halves. All right, So we're going to set 'let's start changing this stuff. 3/2. And we're going to just leave the delta and lambda where they are. All right. Now let's check the size of WQ plus 1R. And L3. So I claim that this is actually less than the L3 norm of this times the L3 norm of this. And it's as if I've cheated using Holder's inequality, but the reason I'm allowed to cheat is because I can use that. I can use a sort of decorrelation estimate, which says that, roughly speaking, since RQ has maximum frequency lambda q, and WQ plus 1R has minimum frequency lambda q plus 1 RQ, right? We set up this strict W to have minimum frequency lambda q plus 1 RQ. As long as RQ is bigger than lambda q plus 1, lambda q over lambda q plus 1, then this number here, lambda q plus 1 times RQ, this is greater than lambda q. All right, so the LP decorrelation says that when I have a function which oscillates at maximum frequency lambda q, and I have a function whose minimum frequency is bigger than lambda q, then they decorrelate. And the idea is that if I have two functions which are saturating Holder's inequality, why are they saturating Holder's inequality? It's because their peaks overlap. But if I have functions which are oscillating at separated frequencies, there's no way for the peaks to overlap or align. The peaks are always randomly distributed amongst one another. There's no correlation. This is a decorrelation. All right. And so the estimate that you get here now is the square root of delta, but now we pay L3 on here. And L3 on there is RQ to the 2 over 3 minus 1, which is RQ to the minus 1/3. All right, we're getting close to the punchline. I promise. What's the correct size for phi q? Well, phi q is like the low frequency part of WQ plus 1 phi, I guess with the 1/2, against WQ plus 1 phi squared. And this is an object which we're trying to measure in L3, which means we should measure phi q in L1. Scales like velocity cubed, and velocity is measured in L3. And how big should it be? Well, if phi q scales like WQ plus 1 cubed, then a natural guess for the size is the cube of this. I already have a guess for how big the WQ plus 1 should be, coming from what I know about how the Reynolds works. And now we're very, very happy because we have just made the allowable size of phi cube bigger than it used to be. And we were having trouble with this current Nash error. It wasn't small enough to fit into the next current error. But now we've made the allowable size of the current error bigger. So we can hope that maybe this is going to help us. And this is, in fact, what saves the day. So let's finish off this claim. And this will lead us to the Goldilocks amount way of intermittency, and I guess we'll stop there. All right, so step 3 and step 4 are how big or how small should RQ be. And let's do this one. How small can RQ be? In order to check this, we're going to check the Euler-Reynolds oscillation error, which, if we remember how oscillation errors work, is supposed to look like divergence inverse of the previous error times the projection off of the mean of some high frequency shear. And I'm going to forget about tensor products, just think of it as something that I'm squaring, right? I square the high frequency thing, and I take the gradient of the previous error. That's what these oscillation errors do. And now let's estimate in L3 halves. All right. Now, let's be super optimistic and think that the divergence inverse is just going to spit out a lambda q plus 1 inverse. Notice that this thing has smeared out frequencies. So its frequency support is not just at lambda q plus 1. So this is extremely optimistic, but let's just assume that we can do the best that you could expect, which is lambda q plus 1 inverse. What do I get here? I get delta q plus 1 lambda q in L3 halves. And if I use my LP decorrelation again, and I measure this in L3 halves, L3 halves of this thing squared is kind of like taking the L3 norm and squaring it. And the square of the L3 norm was RQ to the minus 1/3, which when I square it is minus 1/3. All right, so I'm just using the estimates that we've written down for this WQ plus 1. And I have now paid for making phi q plus 1 bigger by damaging the estimate that appears in the quadratic term. This makes sense, right? When I estimate something which is quadratic, but I've set up my whole iteration to work in L3, I'm going to pay, and this is the cost, is this negative power of bar. All right, so how big, or I guess how small can RQ be? Because as RQ gets smaller, this gets bigger. All right. So I claim that this is the optimal inequality that I can expect if I want one-third of a derivative. And the reason is this gives me 2 beta b squared. This gives me minus 2 beta b. And over here, I have from the lambdas 2/3 b minus 1, which tells me that beta is less than 1/3 b. All right. So RQ has to be bigger than or equal to lambda q over lambda q plus 1.
Okay, so you want to reach this because for other reasons you cannot go above. This is your point.
This
Is a way to
I'm just figuring out
Yeah.
what's going to give me something which is commensurate with 1/3. I.e., how small can RQ be? And the smallest that it's allowed to be is a half power of these lambdas. Because if I take this and I flip it so that it's a negative power, and then I raise it to the 2/3, 2 vanishes, I get 1/3, and I'll end up in this regime. All right. Step 4.
Can you leave this blackboard?
Sure. Let's get rid of this one. And then we'll stop, I guess. So we still haven't gotten to wavelet series, but we will get to it tomorrow. All right. At one point in the lecture, I told you to file something away in your memory. And that was this current error, RQ plus 1, WQ plus 1. How big is it now? This was the current error. Which gave me this never going to work delta Q plus 1 to the 1/2, delta Q plus 2, which is never going to be less than delta Q plus 2. All right, how big is it now? Oops, I'm not measuring an L3 halves. It's a current error. So I'm measuring an L1. L1. So I put 3 halves there, and I put 3 there. I just do Holder. These things aren't separated in frequency, so I'm not going to get any nice decorrelations. Here I get delta Q plus 1. And here I get delta Q plus 2. And here I get delta Q plus 2, delta Q plus 1 to the 1/2, RQ to the minus 1/3. And I want this to be less than delta Q plus 2 to the 3/2 RQ plus 1 inverse. That's going to be the best we can hope for. And I'm already at 4 o'clock, so I'll suppress the arithmetic. But if you do the usual thing and you write this out in terms of lambda q, and you choose the smallest possible value of RQ, that we saw from last time, from this step, what we get is beta less than 1/3b, or maybe it's 1/3. I think it's 1/3, doesn't it? Plus b minus 1/2. This converges to 1/3 as b goes to 1. Okay, so we found the Goldilocks amount of intermittency. It's RQ equals lambda q over lambda q plus 1 to the 1/2. And it's the unique choice which balances this step and this step. And when we found this, I mean, we were so excited. I mean, this is, I see no reason why this should just work. And not only does it work in this specific setup, but I mean, this is robust. So if you switch to any other dimension and you change the number of, directions that your shear flow is oscillating in, and you change the Bernstein, and you change everything in the whatever way is commensurate with the dimension that you're working in, there's always one allowable choice of this intermittency parameter. And I mean, when we wrote down this estimate, we thought we were done with the whole proof, because we found, one of the scariest error terms, which was never going to work in C alpha. And we found that there was a unique way to make it work in B1/3 range. Now, the reason we're not done is because when we smeared out the frequency support of this thing, we ruined this estimate. This estimate is only true at the very highest frequency shell of this object. This object has frequencies much lower than lambda q plus 1. And so we're going to have to fix that. And the way to fix it is to shift our point of view from just purely frequency-based iterations to a more wavelet-based iteration. Okay, so we'll pick up with the wavelet-based iterations on Thursday, and thanks for your attention again.